Okay, so on the mock final exam, question 11 is the work problem. And this one, we're going to draw out a bunch of pictures and then talk about how we can think about it. And let's see, so it says we have a tank in the shape of a square pyramid. So the square pyramid is going to look like, got a base that's a square. Okay, and then it has a vertex here. Right, so our shape looks like that. The pyramid is 20 meters below ground. So this right here, this is our ground. This is 20 meters below ground, and it has a height. The pyramid itself has a height of 40 meters, and it has a base width of 80 meters. Right, it's a square, so the it's 80, 80, 80, 80. Okay, and it's filled to a depth of 30 meters. Okay, and it has a liquid that has a density that's 800 kilograms per meter cubed. So 800 kilograms, this is a mass unit. So that's kind of a clue that we're going to have to start thinking about gravity when we calculate our force on this. Okay, so let's just remember our gravity. This is in metric, so our gravity is 9.8 meters per second squared. Okay, so I'm going to use that as my metric. Okay, so the question is, we want to calculate the work required to get the liquid from the tank up to ground level. So I personally don't like these problems. I think it's better when the tank is just below the ground level, because I'm just going to assume that I've got a little hose and it's going to, transport this up the next 20 meters, right? Because I've got this whole geometry that I need to think about, right? How am I going to get this liquid here up to the top of the tank? And then I need to go an additional 20 meters on top of it. But what I'm going to do is I'm going to make the assumption that the geometry is the same, which is one of the reasons why I don't like these problems. But we're just going to set it up and assume things are okay. Okay, so this is a square. So the area of our base, right, is equal to, we're given it in terms of width. So I'm going to go width times width, right, width squared. Okay, so what I need to do though is I need, like we did with the cone problems, I need to think about, I've got a base here. This base is 80 by 80, but if I go up just a little bit, it's going to be, some other dimension. It's going to be slightly smaller, and it's slightly smaller as I go up towards the apex of my pyramid. So I need to have a way of relating the width of our pyramid to the height of the pyramid, right? I need to have a way of a function for that. So it's facing this way. So I'm going to be, again, thinking about essentially similar triangles. So I'm going to just kind of flatten it out like this. So if I've got an 80 as a base, right, and then the height of my triangle is 40, and then I've got another triangle here, okay, and then the height here is going to be, let's draw it out this way, the height here is going to be how far up did we go, right, and then that's going to be 40 minus the height is going to be the difference here that's going to give me that. So I've got this big outside triangle and this little inside triangle, and those are the two similar triangles that I need to be relating to one another. So I'm going to say my width over its actual width is 80, right? And then the variable is going to be 40. I'm into out of space here. So this w squared 40 minus my height all over, right? The height of the actual. So this is my actual measurement. These are my variable measurements. This is what I need to solve for because I need a way of relating the width to the height itself. So then when I do this, I'm going to get 80 minus h over 40, right? I can cross, cancel these things out. So width is going to equal to 2, 40 minus h. Okay, so keep that in mind because we're going to need to square it, right? So this whole thing, right, this whole thing is going to get put into the squared version here. Okay, so let's think about that right now. So the area, this is our cross-sectional area. Cross-sectional area is going to be w squared. So let's do that. I'm going to call that 40 minus h squared, which is equal to 4. I'm going to square the 2. So 40 minus h squared. Okay, so that's going to be my cross-sectional area. Now I need to think about what's actually happening, right? So I've got my total height that I need to go from the bottom all the way to the top. It's going to be 40 plus 20. So the total distance that this needs to travel is going to be 40 plus 20. So that's 60, okay? But like we've done before in some of the previous problems, the liquid here isn't traveling that full distance, and whereas the liquid here at the bottom is traveling the full distance. So I need a way to relate, right? So this cross-sectional area is going to go the full distance, whereas this cross-sectional area here, it's going to go some, slightly different. So it's going to depend on where we're actually at. So this is going to be 60 minus h in terms of the total distance that we're trying to go, right? Because this is going to depend on where your cross-sectional area is located. Okay, so that takes into account the variation in, like, as we're progressing up through all these little slivers of water, or slivers of liquid, we don't know it's water. Okay, so now, so our force, our work, right, is going to be force times distance, okay? So when I go to think about my force times distance, I'm going to say, right, the liquid is at from 0 to 30, okay? And I've got 4 times 40 minus h squared. This is the area, cross-sectional area, right, of that, pyramid as we go. This is the distance that we're actually traveling, right? And then I need to multiply it by the density of the liquid that we're working with, which in this case is 800. And now I have to take into account gravity, 9.8, okay? And this is going to be dH. I think the solutions have called it x, but it doesn't matter, okay, dH. So now when I put all the numbers together, what I'm going to get is 0 to 30, and I'm going to multiply out 4 times 800 times 9.8, and I get 31360, and I get 40 minus h, let's call it x, so it's multiple choice, we want to make it look like consistent. X is just the distance, that we're traveling, so I'm just going to substitute the variables squared, and that's going to be 60 minus x, and this is going to be a dx, okay? So when I look at the solution sets on here, I don't see it, right? The only one that I see that's 0 to 30 is question C, part C, but then part C has the coefficient on part C is 3200, which means all they did was multiply 800 by 4. They forgot to multiply by gravity. So then that's incorrect. I can rule that part out. The other parts, we need to take into account that I've got, basically I need to have some kind of a cubic unit that I'm working with here as I go. So some of these I can rule out as possibilities. But let me tell you how I actually was able to confirm that this one was the same answer as one of the answers on there, even though it looked different. What I did was I plugged it actually into my calculator. See, I'll show you. So let me bring it up. So here's what I plugged into my calculator. I have on my calculator, I've got the math button. I'll bring it up in just a minute. But I'm going to integrate from 0 to 30. This is my answer, right? This is my coefficient. Let me do this, bring this down. So, so I'm going to integrate from 0 to 30. This is the coefficient times, right, 40 minus x quantity squared times 60 minus x, and I'm integrating with respect my variable dx, right? And when I do this, I get 3.316 times 10 to the 7, times 10 to the 10. Now, in checking all of the possibilities on the solutions, right, I took question part A, answer for part A, and I put that one through. Okay, so this is the equation for part A, and I put that through my calculator as well. Oops, all right, so my calculator is getting confused now. So I'm going to integrate from 10 to 40. I've got this coefficient, I've got x squared, x plus 20. It all looks completely different from what I wrote, dx, but then when I integrate it, right, this is the answer that I got. It's the same number as what I got before. So even though I set up my integral differently, okay, then one of the solutions that's on there, it gives the same actual value, okay? And the reason is, the logic on actually creating it, was that the pipe's coming down from the top, so we need to integrate, which part is getting the, sucking the liquid out first, I mean, there's all sorts of different ways of setting this up, but a way of checking on a multiple choice to see if your answer, okay, is one of the other ones, is in this particular case, you can do it on your calculator. You can check your answer, actually get a numerical value, okay, from your integral, and then check it against all the different possible integrals that are on there, and see if the answer is the same from anything that you have, and none of the above is not an option. Then go back and check your math, and then see if you've made a mistake somewhere else. Okay, so this is that's our mock final question 11.